Here's x, f prime, f of x, and the second derivative. So the domain is everything. It's a polynomial function. So now let's find f prime, which is 3, but it will cancel with 1/3. So this is x squared plus 6x plus 9. This is really nice because I see that this is x plus 3 everything squared. So it will be 0 when x is -3, but it will be always positive otherwise. Which means I have to make sure that the function is always increasing. When its derivative is positive, the function will always be increasing. Okay, let's look at the second derivative, which is 2x plus 6. And when I set that equal to 0, of course, it happens that I get x equals -3. But when I study the sign of this, and I plug in -5, this will be negative. When I plug in 0, because 0 has to be in the table at all times, in all tables, then when I plug in 0, it will be positive. I immediately know that the function has to open downward when the second derivative is negative, and opens upward when the second derivative is positive. When I plug in -3 in the function, let's see what we get. So -3 cubed is -27, so it will be -9, and then plus 27, minus 27, very nice, plus 2. Okay, so that's -7. I need a number here, because this point is an inflection point. The first derivative does not change sign, so it cannot be a local max, local min. But the second derivative changes sign, so it will be an inflection point. So when x approaches -infinity, I know this will be -infinity. When x approaches infinity, I know it will go to infinity. Because at infinities, only this term, the most powerful term, counts. It will dictate. Okay, so now from -infinity to -7, yes, that's true. From -7 to 2, yes, increasing, that's correct. From 2 to infinity, yes, that's correct. That's all you need. You don't have to put anything else in writing. It's very clear to me that you will say that the function is increasing on -infinity to infinity. You will say that the function is opening downward between -infinity and -3, and it's opening upward on the interval -3 to infinity. But you don't have to write all this. I can already see it. But once you put the symbol here, and you put your arrows, and you put the sign, I don't need anything else. So this function doesn't have a max min. It only has an inflection point at -3, -7. If we want to graph this function, let's do that. So 0, 2, that's 1 point, -3, and -7. 1, 2, 3, 4, 5, 6, 7. I did not determine the x-intercepts. So I have to determine the x-intercept. So there must be an x-intercept here between -7 and 2. There must be an x-intercept here. So I should be able to determine those. There is only one. Okay, so it's opening down, and then it changes sign, opening up, and going all the way, crossing the x-axis, crossing the y-axis, all the way to infinity. And I should be able to determine that. Maybe not algebraically, but with a calculator. Very good pick. Thank you. That's what I wanted. Great job. Anything else? Do you want to go back to limits? More limits or not? From chapter 1. What about 20 on 182? Any questions on this? On the previous problem? Okay, 20 on 182. So this is limit as x approaches negative 7 from x squared plus 2x minus 35 over x plus 7. When I calculate a limit, what do I need to do first? What do we always do? Plug it in. Okay, very good. I see the denominator, it will go to what? Excellent. What about the numerator? Awesome. Excellent, I love it. L'Hopital's rule. Limit as x approaches negative 7. The top is 2x plus 2. The denominator is 1. When I plug in negative 7, 2 times negative 7, negative 14 plus 2, negative 12. Done. But L'Hopital's rule has limited applicability. Only infinity over infinity, positive, negative, it's not important, or 0 over 0. It's not used in any other case. It's not applicable. Is there any topic that you would like to go back to? So we said limits, the first derivative, with differentiation, piecewise defined function, derivatives, with the definition. Okay, max min here, concavity. I'm going to add it in. That's it. Anything else that you would like to go back to? And what we just looked at, implicit differentiation, not the second derivative. Well, this is included in derivatives, but implicit. Only dy over dx. Not the second, not d2, y over dx2.